On example 1310, they have a string that's vibrating in the first harmonic mode. That means it's vibrating with the perfect frequency to produce this standing wave with an antinode at the middle and two nodes at the end. It says the string is 1.3 meters in length and it has a frequency of oscillation of 7.8 hertz. They ask for the wavelength and the speed. Well, the wavelength that they're showing here is half a wavelength. If I want to show you the full wave, I'd have to have you use your imagination and go over there something like that. Now, that means that the fundamental wavelength is 2 times the length of the string. And so we're going to go 2 times that 1.3 meters, and that's going to give us the 2.6 meter wavelength number 1. Now, what's the speed of the waves? The wave speed, as we've known for a long time, is the wavelength times the frequency. Now, it's a corresponding wavelength and frequency. So that means that wavelength 1 and frequency 1 multiplied together will give you the wave speed. Wavelength 2, frequency 2, 3, 3, and so forth. Here we're dealing with wavelength and frequency 1, the fundamentals. So I'm going to take the fundamental wavelength, 2.60. I'm going to multiply by the fundamental frequency. They told me that was 7.80 hertz. And whenever I do that, I get 20.28, 20.3 with significant figures, meters per second. Now, in the follow-up on number 47, they say, suppose the waves had a speed of 22 meters per second rather than 20.3. What's frequency of the first harmonic in this case? Well, it is going to be different because the wave speed's different. Just in passing, I'll say, how would you get the wave speed to be different? Stop the video for a second and come up with an answer to that. Okay, we're back again. I hope that you said to get a different wave speed, you would either make the string more tense, that is, make it stretched a little bit farther, or you'd have to switch the string out for a string that was thinner for the same amount of length. Remember that the wave speed on a string is the tension divided by the mass per unit length, or linear mass density, and the square root of that quotient. That doesn't really come into play here, but it's a nice follow-up. For us, though, we're just saying that if the speed of the waves is now faster, that's still going to be equal to the wavelength 1 times the frequency 1. So frequency 1 is wave speed divided by fundamental wavelength, and so 22 meters a second by the same fundamental wavelength as before, 2.60 meters, and that's going to give us an 8.46 hertz. In number 48, they say a guitar string plays flat, that is, its frequency is lower than desired. To get the guitar string in tune, should you increase or decrease the speed of waves on the string? Well, so we have a frequency that is too small, and we want the frequency to be a little bit higher. Now, the wavelength is something that's predetermined because of the length of the string and because of the size of the instrument. And so we're not going to be able to mess with the wavelength. It's going to stay where it is. So to get this bigger frequency, I'm going to need to have a bigger wave speed. What I mean by that is I'm going to multiply both of these, this flat frequency by the wavelength and the bigger frequency by the wavelength, and those are the same wavelength. So this product on the left is going to be a smaller wave speed, and that's too small of a wave speed because you're getting too small of a frequency. And the one on the right is going to be the just right wave speed because you're getting the just right frequency. So how can you get that wave speed? Well, if you watch the last question, I talked about the wave speed on a string is the square root of the tension divided by the linear mass density. On a guitar, the strings are the thickness that they are. If you're not familiar with a guitar, all the strings are not the same thickness, but you're not going to change out a guitar string for one that has a different thickness. What you are going to do is you're going to change the tension by turning the tuning peg out at the end of the guitar. And so you can make the wave speed higher by making this tension bigger than it was before. All that is to say, increase the wave speed so that you can increase the frequency. In number 50, it says, a classmate says that standing waves involve both constructive and destructive interference. Is the classmate correct? as a matter of fact, they are correct. They are correct. And if you can see from my picture over here, what a standing wave involves is it's going to be two waves that are moving at each other. They're going to be interfering, but they're the right wavelength. They're the right frequency for the conditions. And so if you watched a string that was doing a standing wave in slow motion, you would see it continue to alternate between, like in number 2, they're showing that there's actually all the destructive interference and the wave is just flat. And then half a cycle later, it's going to go like picture number 5, and it's going to show you the constructive interference happening at these antinode spots. And so it's the constructive interference is really noticeable on a standing wave, and so you start to think that it's only constructive interference, but it's actually continuing to alternate between constructive and destructive and constructive and destructive. So that classmate is correct. On number 53, it says a guitar string 66 centimeters long vibrates with a standing wave that has 2 antinodes. What harmonic is this, and what's the wavelength of the wave? First thing, pause the video and try to draw this for yourself. Here's what I've drawn. It's not beautiful, but there's the 2 antinode second harmonic pattern. They didn't ask this, but what overtone is this? Remember, overtones are higher frequencies that also give you resonance, and the second harmonic is the first time you get one of those higher frequencies. So this is the first overtone. And then in part B, what's the wavelength of the wave? Well, the wavelength of the wave in this case is going to be just the length of the string. The wavelength 1 is twice the length of the string, but now wavelength 2 is just the length of the string. So it's just the 66 centimeters. In number 54, they give you a length of a string, and they give you 4 wavelengths, and they ask which ones could produce standing waves. So it says that the 0.33 meter string is tied to a wall at either end. Which of the following wavelengths produces that standing wave? Okay, so say I have the wall and the wall, and the string is 0.33 meters long. So that means that the fundamental wavelength is going to be twice that length. And so the fundamental is going to look like this. And if I wanted to show you the rest of the wave, I would show you over here. So you can see that this is my fundamental wavelength, and it's 2 times the length of the string, or 0.66 meters. And I don't know what the wave speed here is, so I don't know what the frequency is, but I know whatever that frequency would be, I'd call it F1. Now, similar thing, I could have half of that. So I could have the second harmonic looking like this, and this would be wavelength 2, and it's just the length of the string, so it's 0.33 meters. And I don't know what frequency makes that because I don't know the wave speed, but I do know that it's twice the fundamental for frequency 2. Now, along those lines, if I wanted to triple that fundamental, I could say 3 times the fundamental is frequency 3, and that would give me a pattern that looks like this. And you can see that the wavelength there is 2/3 of the length of the string. And so that wavelength 3 is the 0.22 meters, or 1/3 of 0.66. So I'm ready to answer this now. They said which ones will produce a standing wave. Well, 0.22 does. It produces the third harmonic. 0.33 does. It produces the second harmonic. And 0.66 does, and it produces the fundamental, or the first harmonic. The one that doesn't is 0.44. And you might say, well, you didn't show that there's no 0.44. Well, the only ones that exist are these integer multiples of the fundamental frequency. And so 0.44 would be somewhere in this realm between 1 and 2. But there isn't anything between 1 and 2. So this is never going to work. On 55, they have a string attached to either end of the wall, and they give you the fundamental wavelength of the string. And so I say wavelength 1 is 0.65 meters, and they want to know what's the separation between the two walls. Well, I've drawn this a couple times already today, but you can see that the fundamental frequency is going to produce a wave that looks like that. And so you can see that the fundamental wavelength is 2 times the distance between the walls, or 2 times the length of the string. And so that is the length of the string, or the distance between the walls, is half of the fundamental wavelength. And so that's just going to be my 0.65 meters over 2, and that's looking like 0.325 or 0.33 meters. 95 says a string that's 1 meter long is tied down at both ends. The 3 lowest frequency standing waves on the string have frequency of 100, 200, 300 hertz. What's the fundamental frequency of the string? Well, it's definitely 100. The smallest frequency that gives you a standing wave is the fundamental frequency, so that's frequency 1. This must be frequency 2, and I'm happy that that's two times the fundamental frequency, and this would be frequency 3. So 100 is the fundamental. What is the wavelength of the fundamental mode? Well, the fundamental wavelength is always 2 times the length of the string, and so it's going to be 2 meters. In 96, the speed of waves on a string that's tied down at both ends is 32 meters a second. Fundamental frequency for this string is 65 hertz. So 65 hertz is producing this fundamental wavelength pattern. It says, what's the length of the string? Well, I can very easily figure out the fundamental wavelength, and then the string is going to be half of that, because if I wanted to show you the fundamental wavelength, it would be all of that distance right there. So the wave speed is the wavelength times the frequency. Remember, any harmonic number you want, but it has to be the same harmonic number. And so the wave length is the wave speed divided by the frequency. And so I'll take my 32 meters a second and I'll divide by my 65 hertz. And you can get a 0.4923 meters for that. Now again, that's way too long. That's from there all the way over to there. They want the length of the string, which is only half of that. Again, 2 times the length of the string is the fundamental wavelength, so the length of the string is half of the fundamental wavelength. So how about half of 0.4923 meters? And that'll give me 0.2462 meters, 0.25 meters.